All right, so F net though. F net on the 2 kilogram object, well, it's a projectile. And what that means is W is the only force. There is no friction, no drag, nobody blowing on it, nobody shooting it with sand. There's nothing else going on. This is the only force, right? It's the only reason that the object's motion will change. It's the weight force. So this is mg. That's how you calculate the weight force, where g has something to do with that. But I want to refer to my coordinate system, so I'm still following my nose. I'm not sure that I can get through to the end, but I'm starting to see that I kind of know a lot of stuff. So let me continue. So this is what gravity, or the weight force, is. This is 2 kilograms, that's the m, and then g is 9.8 meters per second squared in the minus j hat. It's down, right? Weight forces are down in this projectile motion. So the weight force is down. So I'll make it down by using the minus sign, and I make it a vector by referring to the unit vectors that this velocity is actually referred against. So you can see that I have a value for the weight force. What's really cool is no dependence on time. So this function that in general can be time dependent, which is why it's inside the integral symbol, if it doesn't have anything to do with time, if it's a constant in time, then it's a constant in the integral, even though it's a vector. And you can take this vector that is not dependent on that variable that's being integrated over, you can take it out as a common factor on the rest of the integral. So j net, so I'm just following my nose, and I honestly, I sort of see through the problem now. And maybe you are beginning to see that you can finish this problem. But anyways, so this is the net impulse from A to D is only due to one force. It's the weight force, and it's the weight force acting for the time that takes me from TA up to TD, which is 4 seconds. But I don't know TA, I don't know TD. I'm not really sure what to put at the bounds of the integral. So this, though, is F net on the 2 kilogram object, integral dt from TA to TD, which is F net on the 2 kilogram object, right, times, so the integral of dt is t, and t is evaluated at TD minus TA. So the net impulse delivered, which is the only missing piece so far, is calculated here as 2 kilograms times 9.8 meters per second squared times minus j hat times 4 seconds. I've got all of the details to calculate j net. So let's finish this. So let me pull the paper down. You can kind of see where we were left off. So we are still looking for our goal is P sub D, but we know this, so P sub A is easy. We just wrote it here. It's 2 kilograms, right? Here's P sub A. 2 kilograms times that initial velocity, or the velocity at time A. So it's 3 I hat plus 4 j hat meters per second. So here's a mass times a velocity vector. And then we add, so P sub D, is P sub A plus j net. So let's add on j net. J net is this business right here, right, that we calculated. We had to think about net forces and stuff. We had to still be a physicist, even honestly referring to Newton's second law for a minute there, or at least the free body force diagram for it. So we just have to fill in this. So we've got to add this thing. You can see has its own minus sign, but the instruction is to add it. These are added together. It just happens that J is negative. So 2 kilograms and then 9.8 meters per second squared. There is a minus J hat, and there is this 4 seconds. So we're done with that page. Okay, yes. So here's piece of D. That is our original problem. We didn't know if we could solve it this way, but lo and behold, we followed our nose. We didn't make any math errors. We were very careful with pluses and minuses, directions, all the details. Didn't make any mistakes as far as we know. So didn't take anything for granted either, right? We used, yeah, everything's very careful. So at this point, just because I'm kind of the instructor in this video, I'm going to peel this thing apart into X direction and Y direction. So in the X direction, it's everything that has to do with I hat, right? That's the X direction stuff. So in the X direction, it's 2 kilograms times 3 meters per second in the I hat. So that's the only thing that's in the X. All right. In the Y direction, it's 2 kilograms times the 4 meters per second. So in the Y direction, there is 2 kilograms times 4 meters per second. And this is in the J hat. That's one of the Y direction pieces. But the other Y direction piece is from over here. So I'll put this minus sign out front finally. So this is minus 2 kilograms, 9.8 meters per second squared. So there is a little multiplication here. And then there is 4 seconds. Don't forget that there is this delta T that's being tacked on. It's this delta T times this force, this net force. So there is 4 seconds. I'll just put it there. And then there is the J hat again. And I have already moved that minus sign out front. Here's the minus sign. All right. So if you look at this really carefully, this is a vector that is 6 kilograms meters per second towards the right, right? There's an implied plus sign there. And we're adding 2 times 4 is 8 kilograms meters per second. Positive J hat is an arrow. So this arrow is meant to represent that 8. This is a 6. So this thing is bigger than that thing, right? And it points up. And then we are subtracting off. And at this point, I forgot to bring my calculator in here, and my phone is being used as the camera. So I'm going to do a little bit of longhand multiplication. So I want to subtract off, right? Or add. I'm going to, watch this. I'm going to add this arrow, which is a downwards pointed arrow. But let me figure out how big it's got to be. So 2 times 4 is 8. So 8 times 9.8. You can watch me do some math. So 8 times 8 is 64. There's the 6. 8 times 9 is 72, plus a 6 is 78. Like this. And there is a tenth. So this is 78.4. Kind of makes sense. It's 8 times almost 10, which is almost 80. Here is almost 80. So 78.4. So 78.4. So it's kind of going to be kind of crazy, but let's, I can't draw it on here to scale, but there is a minus J hat is a downwards arrow. And that downwards arrow has a length of 78.4 kilograms meters per second, right? So I want to add these three vectors together, and what this looks like is, check this out, this is, actually, this is what we started with momentum. This right here, according to the Impulse Momentum Theorem, this is actually just, we calculated the impulse. It was the result of calculating this integral. We calculated impulse. The Impulse Momentum Theorem says that if you are able to calculate the net impulse, what you know is that the momentum will change by that amount that you calculated. So this is the change in the momentum. So we start with this arrow. This is piece of A, right? It's 6/8 up, and we are adding on this arrow, delta P, which is the 78.4 down, and this plus this. Let me show you what it looks like on the side here. So this plus this really, really big downwards arrow. This is delta P, this is PA, is equal to, it's equal to the connection, right? This dashed line from that tail to this tip. So let me try to draw it to the side here. So this is P sub D. It's the result of adding P sub A plus the change, where the change is the impulse. So here's P sub D. And now let's look at this. Here's P sub A, points up to the right. And after acting for 4 seconds, gravity acted for 4 seconds, we get a final value of the momentum that's down to the right and large. Here it is. It starts up to the right, small, and 4 seconds later, it's down to the right and very long or large. This is the Impulse Momentum Theorem for projectile motion. This was all just for one problem, this problem number 1. But let's do another problem. So the other problem is this. We're going to have to mix in some kind of pre-knowledge. And I'll describe what I mean by that. But here's the problem. The problem is how much time does it take for projectile to go from A to B? How much time does it take the projectile to go from A to B? So let's go look back at A to B. So here's A, that's the starting point. We know some details about A. We know the motion, we know the mass, we know that there's gravity. So the question is how much time does it take to go from A to B? And you'll notice that there is no time given. This stuff we just solved is for D. It's between A and D, so that's not really applicable to our problem from A to B. So how much time does it take the projectile to go from A to B? You know, if you knew TB and T sub A separately, if you knew these things, then you don't even have to use the Impulse Momentum Theorem. You just take the subtraction of these two different times. But you don't know either of those times. What you do know, though, is the answer to this question actually is this time interval. This is the answer to the problem right here. So delta T from A to B, if I can figure out a way to find this, then I can, the answer to this value is the same as the answer to the question.